Welcome to week 4 of thin film deposition module. In previous lecture we discussed how an atom or atom of the thin film that we want to grow interacts with the surface on which we want to grow the thin film, okay. And we discussed two different isotherms of which relate to the adsorption, and then we discussed nucleation part, okay. We will go forward with nucleation and growth in this lecture. So, in the previous lecture we had discussed how the free energy change and the fact that d del g over dr should be equal to 0 for either this to become a critical radius, right. So, this is the change in free energy with the radius of the nucleus. So, in the beginning when the nucleus is very small, the free energy change is positive, okay. So, and free energy change whenever is positive, it is not an equilibrium process, right, because it will not continue forever, okay. The free energy change for forward reaction is always negative. So, there is a critical radius and critical energy beyond which it will start to have change which is negative, and then we will get a stable nucleus, okay. And these critical radius and critical free energy change is given by these two expressions, okay. We can further simplify this change in free energy expression as 16 pi gamma FV whole cube divided by 3 delta GV square, okay, and 2 minus 3 cos theta plus cos cube theta divided by 4, okay. So, I have converted all the surface energies into surface energy with FV using the term theta, okay. We can do that because at any point if this is my angle with theta, right. So, my surface energies were, this is gamma FV, gamma FS, and this is gamma SV, right. So, we can so these are the three different forces acting at an angle theta, and we can have the relation between them by resolving this into cos and sine components, okay. So, we can get this expression. Now, if theta is equal to 0, right, then we say you can see from this, if theta is equal to 0, then this whole term becomes 0, which means delta G star is equal to 0, okay. Then there is no energy barrier for a growing nuclei to overcome, right. It is spontaneously, there is no barrier for nucleation, okay. There is no energy barrier for a growing nuclei to overcome in order to become a stable nuclei. Even a single atom sitting on the surface is stable, okay, in this condition, okay. But if delta G star is not 0, then several atoms have to come together to form a stable nuclei, okay. Okay. In the second term, if theta is equal to 180 degrees, then this term will become 1, okay, and then you can relate it to homogeneous nucleation, okay. So, this will become homogeneous nucleation, okay. If the free energy change is 0, then you can relate it to homogeneous nucleation. So, these are the two different extremes of this. Now, the expression for change in energy delta G that we had discussed in last lecture, given as a 3 r cube delta GV plus A1 r square gamma FV plus A2 r square gamma FV minus A2 r square gamma Fs. Okay. So, this was my my expression. Let me double check. Sorry, gamma. Sorry, this is SV. Okay, this is Fs. This is the surface being formed, and this is Fe. Okay, so this was my expression, which is a generalized expression. If you have any other energies or acting on this, then you can add that energy to this, and how this energy changes with the radius, that factor you can add, and then use this expression to recalculate what would be the size of a critical radius or a stable nuclei. Okay. So, you can do that by adding any extra energy terms. Okay, you can add them here. For an example, if I have some strain energy, okay, if there is a lattice mismatch for an epitaxial growth between substrate and the thin film, then I will have some strain energy, right. So, and this strain energy will again depend on the volume of the thin film. So, this is volumetric thin strain energy. So, let us say this delta Gs, this change in delta G because of strain energy is volume component and delta Gs. So, this is strain energy. So, we can add this strain energy to this term and then calculate the critical radius. Okay. And so, I will not go into that, but you can keep adding different energy terms which come into play when you are forming a thin film. Okay. Now, we look at different modes of thin film growth, okay, because there are interplay of different surface energies, okay, and in between these two extremes. Okay. So, we will discuss thin film growth modes. Okay. Now, we will start with Young's equation, which relates different interface or surface energies such as gamma SV is equal to gamma Fs plus gamma Fv cos theta. Okay. Now, for reference, I must also plot that this is my surface, this is my nucleus, okay, which is making an angle theta. Okay. Radius is given by this, okay, and these are different energies. This is gamma Fv film and vapor, this is gamma Fs film and substrate, and this is gamma Sv substrate and vapor. Okay. This is substrate, film and vapor. Okay. So, and this is my Young's equation. Okay. Now, there are three distinct modes in which this thin film can grow. Okay. First one is called Vollmer Weber thin film growth or island growth mode. Okay. So, for this condition to happen, for this growth mode, theta is greater than 0. Okay. So, it is not wetting, okay, and also gamma Sv is less than gamma Fs plus gamma Fv. Okay. So, suppose for example, I will neglect gamma Fs, okay, because this is film and substrate. If suppose they are similar materials, okay, then gamma Fs can be neglected. Now we have gamma Sv and gamma Fv, okay. If gamma Sv, the surface energy between substrate and vapor, is less than surface energy between film and vapor, right. So the substrate will I mean the whole system will like to have more area which has surface and vapor, okay. So it will like to have, because this surface energy is lower. So what would happen in that case? My thin film growth would happen in form of islands, okay, like this. And once one layer of islands is formed, then second layer of islands, and these islands will then start to merge and make a continuous film. But the growth mode will be from islands, okay. That is why it is called Vollmer Weber island growth mode, okay, and this is this condition, right. And to give you an example, when you put oil on water, the oil starts to become droplets, right. So it does not spread. So that is the same thing here. It will try to become like balls, islands, okay. These are islands, okay. So this is one of the conditions for Vollmer Weber growth mode, okay. Second is it is called Frank van der Merwe, okay, Frank van der Merwe layer growth mode, okay. This is the other extreme of the growth mode, where your contact angle theta is roughly equal to 0, okay. In this case your gamma Sv is higher, okay, that is surface energy between substrate and vapor is very high compared to gamma Fv, okay. Again I am neglecting this for simplicity, or it is even higher than, because this is plus gamma Fs, okay. So it is higher than these two energies combined, because when you have this layer growth, you are eliminating this surface and you are creating these two surface energies, right. So this energy is much higher than or surface energy is much higher than the combined of these two. So what would happen for the growth for the deposition? It will form layers, right, because this system will not like to have exposed substrate vapor interface, okay, because this surface energy is very high. So if there is more exposed surface vapor interface, then this system would have more energy. So in order to reduce energy, it will form layer growth. So a small amount of material will form a thin film, okay, spread out, okay. This is the spreading of any liquid onto a surface which has lower surface energy, okay. So this is the other extreme, where the surface energy between substrate and vapor is very high, so the layer growth mode happens, okay. There is a third mode which is called Stransky Krastanov growth mode, okay. We will discuss what this growth mode is, and this is a very complicated mode. It is not completely understood, but there are some insights into it, okay. And this growth mode is layer to island, okay. So in this growth mode, first few layers are by, so this is my substrate. So in this growth mode, first few layers are in layer to layer growth. So first layer, second layer, and then it switches to island growth mode, okay. So, this switch from layer to island growth mode must have some extra energies involved, right. So, we will discuss this part and why this happens. We will discuss one of the possible cases, there could be many other things. Okay. So, this is called Stransky-Krastanov growth mode, from starts with the layer to layer deposition and then switches to island growth model. Okay. Now, for this let us discuss if gamma SV is higher than gamma Fs plus gamma Fv. Okay. If it is higher, this then we will have layer growth, okay, right. This is Frank-Dermurray layer to layer growth model, okay. But after few monolayers, there are some energies which come into play which change such that your gamma, suppose this gamma Fs between film and substrate, this increases, okay, due to layer growth. Okay. Then in a condition, then this SV will, or there is no SV left, then what would happen, because in layer growth your substrate to vapor is already gone, that interface is gone. So, you are left with two interfaces, okay, gamma Fs or gamma Fv. Okay. So, after this layer growth you have two interfaces left, okay, between film substrate and film vapor. Okay. So, which one it would like to increase? So, suppose again let me draw this here again. So, this was my substrate. Okay. Initial growth happened due to Frank-Dermurray growth of layer by layer. So, this layer is grown, okay, let us say to or certain thickness, okay, and after this you have this gap shaped. Okay. Now, if you see that there is no more substrate to vapor interface, so we can neglect that part. Then the interplay between the two, either film substrate or film, either this interaction is high or this interaction is high. Okay. So, this in this case this will become gamma Ff, right, between the film and film, right. This interface is film and film because they are the same material, okay, and this film vapor is still, so this interface is film vapor and this is also film vapor. Okay. Now, if this energy is small, okay, so if this energy is small, then it will try to maximize this area by forming these islands, okay, and that is why you will have layer to layer growth and then island growth. Okay. One of the example why this change could happen is because of the strain energy in the layer thickness. Okay. Let us look at that. Okay. Stability of strained layer. Okay. So, suppose we have a let us go back to epitaxial growth model, okay, and we have a lattice mismatch, and this lattice mismatch will give you some strain energy. Okay. Now, strain energy in film we can write as Gs, okay, where Gs would be equal to 1 by 2 Young's modulus the strain. Okay. So, is the strain and this is Young's modulus for the thin film plus for thin film. Okay. So, this will be my strain energy. Suppose if I had a mismatch between the substrate and thin film of F, which is equal to A0 substrate minus A0 thin film divided by A0 of substrate. Okay. This is the lattice mismatch, and this lattice mismatch is due to the difference in their lattice parameter for an epitaxial growth. Okay. Now, as we had said earlier, we can any energy due to strain or any other thing, we can include that into the delta G term. Okay. So, let us do that delta G. Okay. And for simplicity, I am taking it is a hemisphere. So, theta is equal to 90 degree. Okay. So, this is my hemispherical and this is 90 degree, okay, on my substrate. So, contact angle is 90 degree. It simplifies things, okay, for our purpose to discuss this part. Okay. So, when we do that, this will become 2 pi r cube by 3 delta GV volume change, phase change energy, plus pi r square gamma, okay, plus delta GS. Okay. Now, let me simplify it, just correct this, that this is my thin film and this is my change of color, this is my substrate. Okay. So, this is substrate, okay. This is my layered growth because this is Stransky Krastanov growth and this is island. Okay. So, the interface is only between this and this volume, right. This is my gamma FV, we can write this as FV. Okay. So, this is my total energy change, and we can now discuss change in strain energy delta GS. Okay. Suppose we say that formation of islands releases strain energy of layered thin film. Okay. So, the formation of island is because there is too much strain energy in the layered growth. So, by formation of islands it will release some of that strain. Okay. So, we say that before nucleation my GS was 1 by 2 y f square h. Okay. Let me go back, this is per unit length or thickness. Okay. This h here is the thickness, h is the thickness of layered growth. Okay. So, this was my before nucleation of islands, all the strain due to mismatch was present in the film of thickness h. Okay. After nucleation or island formation, let me not write nucleation, before island formation and after island formation. Okay. So, now GS1 GS2 is 1 by 2 gamma h. Okay. I will say that this is strain after island formation. Okay. So, even after formation of island there is some strain left in the thin film or the layered. Okay. So, this is the change upon formation of island. Okay. So, my delta GS would be equal to 1 by 2 epsilon square minus f square into gamma into h. So, this is my change in strain energy. This is change in strain energy upon island formation. Okay. Now, if you see that say for critical radius of the this island, right, for critical nucleus size or the radius of this island, and let us say that okay, I have to, so if this is my substrate, okay, it is always good to replot things, and this is my layered H, and this is my cap, okay, island, okay, island of radius r. Okay. So, the area of this island would be pi r square. Okay. Now, if I use this delta Gs into this expression, and in this expression here, and again use the same expression for d delta G over dr should be equal to 0 for thermodynamic stability. Okay. I can show that r star in this case will have gamma minus 1 by 2 epsilon square minus f square y h divided by delta G v, okay, and this would be a minus term here. So, this will be my r star. Okay. So, this is the critical radius of stable island. Okay. Now, when is this nucleation start? Because after certain thickness of this layered growth, there will be enough strain energy in this thin film to start the nucleation of island. Okay. So, when r star approaches 0, right, the critical thickness is such that it has enough energy that even a nucleus or island of 0 radius is stable, it is more preferred. So, means my strain energy in the thin film is high enough that even a small radius or island will be stable. So, that is the case. So, in this case we can calculate what would be my H star, that critical thickness where the formation of islands starts. Okay. If we do this from this expression, we can calculate a relation between gamma and H in terms of other parameters, and we will get 2 gamma over epsilon square minus f square into Young's modulus. Okay. So, this will be my onset of Stransky-Krastanov growth, this thickness. We can write this as onset of Stransky-Krastanov growth, okay, or switch from Frank-de-Merwe to Vollmer Weber. Okay. Either way you want to say, if your thickness, film thickness, layer thickness goes above H star, this critical thickness, then the release of energy is more preferable to form these islands. Okay. So, this is the critical thickness for the onset of Stransky-Krastanov growth, which is layered and then islands. Okay. This is many times utilized in epitaxial growth where you want to form quantum dots. Okay. Quantum dots are small nanometer size dots of some semiconducting material, where because of higher confinement the energy levels are more split. Okay. We are not going to discuss that part, but this principle or this growth mode is sometimes utilized to grow quantum dots. Okay, because you manage your lattice mismatch such that after certain thickness of H star you have island formation in your thin film, and you stop the thin film formation, then you will have some quantum dots. Okay, some dots or islands of very small size. Okay, nanometer, few nanometer, 1 to 2 nanometer, which then again confine electrons in that size, which is a quantum dot behavior. Okay. Now, all this information is presented in this view graph, which relates that which growth mode would be more stable if given the changes difference in surface energies, okay, and lattice mismatch. Okay. And it also signifies that what is the region where we should be depositing if you want to deposit super lattice. Okay, I will just come to that. So, if you see that if lattice mismatch is very small, okay, it is 0.3% mismatch or below that, then you will have Frank van der Merwe layer by layer growth irrespective of change in difference in surface energies of substrate and film. Okay. This is S is substrate and F is film. Okay. And these are with respect to vapor. Okay. So, if you have very small lattice mismatch, then you can grow this. Okay. And if you have very large mismatch and the energies are also different, then you will have Vollmer Weber island growth. Okay. In between there is a region where these two exactly match up to give you Stransky-Krastanov mode, which is layer plus island growth. Okay. So, this is a view graph where you can see how the surface energy mismatch and lattice parameter mismatch can be interplayed to change the growth mode. Okay. So, and these super lattices are artificial lattices where you deposit on a substrate. Again, this is an epitaxial growth. Okay. Epitaxial growth of thin films of different compositions, but such that the lattice mismatch is managed. So, what you do is that you have one layer and then you grow another layer. Okay. There will be some lattice mismatch, but you do not go above the critical thickness. So, there is no island growth. Okay. Then you switch your material to a different material. Again, there will be a lattice mismatch, but the strain in these two films is in opposite direction. Okay. Then, so that there is no buildup of strain in these two layers. Then you can switch back to your first layer. Again, there will be some strain, but then you can switch back to another composition of a different material or different composition such that this strain is nullified. So, if one layer has compressive strain, the second layer has tensile strain. So, overall in repetition you can keep building this up, okay, and very thin layers, this would be 1 to 10 nanometer thin, okay, and you can build different layers, and this is what is called a super lattice. Okay. And this has also various applications in solid state optics as well as electronic materials. Okay. So, with this we will stop here for this lecture and we will discuss nucleation and kinetics aspects of nucleation and how temperature and deposition rate change your thin film morphology in the next lectures. Thank you very much.